Swayam Prabha. Digital India. Educated India.
So, we begin again with the first law. Then we mention that if we allow Q amount of heat to enter into the system and the system does W amount of work, then the change of state can be specified in terms of internal energy difference, that is the final state internal energy minus initial state internal energy, the difference we call delta E, and that is basically the Q minus W. That was the first law of, that is we call the first law of thermodynamics. Now the point is that once we talk about this W, and the W is something that's a concept derived from mechanics, and so far we have used only the basic definition of work, that is the force times the distance, that's the mass times the acceleration due to gravity times the h, that is mgh kind of thing. But if we want to apply it for the general thermodynamic system, we need some more clarification about this work and the work for a definite change of state of the system. So, more about work. So, we learn something more about this work W. So, work W. So, you have seen that this work is basically a concept that is basically the force times the distance. That is basically the work done. So, if we take a gas instead of a liquid or water, then there are certain advantages. Then if I change the temperature or the pressure of a gas, it is much more easily manageable, and we get a lot of change of temperature, change of pressure, change of volume. This we can effect on the system in a much more easier way than for an actual liquid or a solid body. So, so for that, and secondly, there is another reason for choosing a gaseous system, because the gas laws are almost universal. That means if you have a gas, no matter it is hydrogen or oxygen or nitrogen, if you keep the density of the gas is low and the temperature is slightly high, then more or less they obey the same gas laws. The universal gas laws are, and two parameters are sufficient to describe the system in terms of PV equal to RT, that we learned from class 12 class 12 curriculum. So that means if I specify two states, that is the temperature or pressure, volume is automatically fixed. If I fix temperature and volume, pressure is automatically fixed. That's why I use only two parameters to describe the internal energy. So that is the main thing, that the two parameters can be easily adjusted. Now, for a gaseous system, it is much more easy, because just to repeat, that is for the laws connecting the temperature, pressure, volume are universal. That is PV equal to R2, universal equation of state. But no such universal equation of state is possible either for liquid or solid. So that's why we take gas as the system for most of our discussion. So if I put the gas inside a cylinder with a piston, and I keep a mass on it, say the mass is m, and there is a gas inside, so it has a, say it has a volume, say it has a, and the mass actually is put on the lead of this piston, on the piston, or this float, and we see that this is balancing the pressure inside. So I call it the, say there is some pressure outside is there, but in this case we have a mass, and if the gas is something that is being, say this is a volume V1, I allow the gas to expand up to a distance, say this 2, and I call this is V2, then V2 minus V1, this shaded area, basically the change in volume. So this V2 minus V1 is the change. If I can adjust my adjust my mass or some other ways. So W is something we know that is mg times h. H is basically the distance. So mgh is the distance. Now we see that if there is an area of the piston, and the area of the piston, if it is divided by this area and you multiply it again by h, then A times h, this quantity is basically what this quantity is. This is there is an area times this distance, means this is the volume that is shown in the shaded diagram, and that is V2 minus V1. So AH is basically a volume that is basically V2 minus V1, and this is basically the force, mg is force per unit area, and that is called the pressure. I call it P opposing pressure, because the gas has been expanded from the volume V1 to V2, which is higher. So gas has expanded against an opposing pressure, P opposing, and AH is basically V2 minus V1. So why I have written this mechanical, I have transformed this mechanical language MGH to some parameters of the system, that is V2 minus V1, and if the P opposing is equal to the some pressure, if I can relate it to some pressure of the gas, then I can relate this W to the some internal parameters of the system also. So that is an advantage. So the pressure times the volume, V2 minus V1, change in volume, or I can write it as P opposing times the delta V. So this means that if I plot this pressure versus volume curve, there is a curve like all this is a rectangular hyperbola kind of thing. This goes to infinity. As you increase the volume, this will meet at infinity, and if you increase this pressure, it will meet to infinity. And you see that if I change this volume, say V1 to V2, and on this particular, this is a point corresponding to my V1, and this is basically P1 pressure, that is, and you so let this is V2. This point corresponds to the volume V2. This is pressure P2. Now see that this is a curve. This is called an equilibrium curve because it is fixed at a fixed temperature constant. If I keep my temperature of the system constant, that is, I put everything on heat bath, and so that temperature remains constant, then if I adjust my pressure with respect to the volume, and if they are equilibrium, that means at every point, at this point, I have kept my P opposing pressure equal to the pressure at P1. And if my opposing pressure is P2, then P opposing, then it corresponds to a volume V2. So if we move along this line, the change is basically the change of equilibrium pressure of the gas. So that has to be very clearly understood. That's a very important statement. That, but other than this, so say if I choose a pressure here, so corresponding I can choose a volume, this volume. So this is not an equilibrium pressure. Say I can pressure opposing, I can choose this pressure at this volume, but this does not correspond to this P1. So it is a pressure much lower than this one, equilibrium pressure. So this is an arbitrary P opposing. So there is when they are equal, the gas is at equilibrium. That is, when the P opposing is equal to the internal pressure of the gas, we call it that there is an equilibrium in the system. So that this curve has to be understood in that sense. So next, what we do here, if I now do the work of expansion, now we come to work of expansion. If we see what is the work of expansion, so for this we come back again to this curve. So this is pressure P, and this is the pressure volume curve, and I want to expand the gas from the volume V1 to the volume V2. So V2 is larger than V1. So I have a say equilibrium pressure here. I have an equilibrium pressure here. This is for the P2. This is basically P1. And if I choose a pressure, say P2 for the volume V1, say I have kept the volume of the gas V1 and chosen this P opposing, I choose my P opposing equal to P2 for V1. So I choose P opposing pressure at this, say, some point, say P2. It is a much lower pressure compared to P1. So at this point, this is a point, and I allow the gas to expand. How much it will expand? It will expand up to V1. I want to expand the gas from V1 to V2. Then V2 minus V1 is my change in volume, and I am doing it against the P opposing, exactly what we defined here, and that is equal to your W of expansion, the one stage expansion, and V2 minus V1, and this opposing pressure I have chosen deliberately to be my P2. So if P opposing equal to P2, then W expansion equal to P2 times V2 minus V1. That is the expansion. And so if it is P2 and this is V2, this is V1, so the gas has expanded from here to here, and the area in the shaded region is basically the work done by the system, because the gas has expanded. We call the system has done some work. So it is an expansion work done by the system. You see that the positive V2 minus V1, and in the P2 is always positive, but this expansion, but I can carry out the expansion also in a different way. Let us, this is my choice, that I have chosen the pressure in that way. And now if I do some different kind of expansion for the same change in volume, again I change the curve. I have the curve, PV curve, PV diagram, and the same change in volume that I want to carry out, V1 to V2. For V1, I have the equilibrium pressure, say this is my V1 and this is my P2. So, this is my P1, this is my P2. Then if I now choose my pressure, say at some intermediate point, say it is P opposing, and say this is a volume V1. I want to expand the gas from V1 to V2, V1 to V prime first and then V prime to V2. So, I go from, for the expansion, V1 to V prime, I need a pressure which is less than P1. So, I choose this, say this pressure P1, and this is my volume. So, the P, this times the P opposing is the first stage of expansion. So, this is an area, this is an area given by P opposing times the V prime minus V1. Sorry, I should write it as V prime minus V1 because in the expansion process. So, V prime minus V1 times the P opposing, I have chosen it lower than P1, so that gas can expand from V1 to V1 prime. So, V1 prime minus V1. Next stage, what I do, I say I keep my pressure, say at P2. So, I keep my pressure at P2, P opposing, I keep, if it is P2, then it is basically P2 in times V2 minus V prime. So, I expand the gas from V prime to V2. So, V2 minus V prime is my change in volume times the P2. P2 is basically this one. So, area the area under this curve by the cross line, shaded line, that is the work. This is again an work of expansion. This is one stage. This is a two-stage expansion. This is one stage expansion. I am expanding the gas from V1 to V2 for the same volume change I am doing here, but I see that the area under the curve is much larger compared to the first one. So, one stage, two-stage expansion gives more work done by the system for the same change of state. So, for the same change of state, two-stage expansion gives more work than that for the single stage. That's very interesting thing. So, in this case, you will see that the work for the same change in volume, the work done by the system are different. So, it depends on how you carry out the process. That depends on how, so that depends on the path for the change from V1 to V2 or the same V1 to V2 at the same temperature. Temperature is always kept constant, T constant throughout the process. Here also the T is the same. So, you see that for the same change of state, I have an initial state, say at the temperature T with a volume V1, I have another state temperature T volume V2. Again we have the same change of state from volume V1 to V2 for the same T1. Both cases, I see the change of state is the same, the work done are different, because it depends on how you carry out the system for the work of expansion. So that's a very interesting thing. So I can there is a lesson behind it. That means if I do some multi-stage expansion, the system can give me more work. So that is a basic philosophy which can be drawn from these two figures, that the shade area given by this shaded portion. So the next thing, we come to the work of compression. The same thing we do to carry out the work of compression. So we draw the same PV curve, PV diagram, and we have the same volume V1 to V2, but here what I will be doing, I will compress the gas from V2 to V1. So V2 to V1 is a process of compression. So this is again the pressure P1, equilibrium pressure P1, and this is the pressure P2, the equilibrium pressure on this PV line. Now, if I want to change the state of the system by one stage, that means V2 to V1, I may choose a pressure that is a compression. I want to compress the gas from V2 to V1. So I must choose a high pressure. The best way is to say I can choose this pressure P1. So if I choose this pressure P1, then P1 and opposing pressure, if I choose P1, P opposing equal to P1, then what happens? Then I am changing the state from V2 to V1. So final state is V1 minus initial state V2. V1 is much less than V2, so it is a negative quantity times the P opposing, that is equal to work of compression for a single stage, and that is equal to, since by choice I have chosen this one P1, so this is P1 times V1 minus V2. This is a final minus initial. And so what is the shaded area? Shaded area now this is a shaded area. So this P1 times V1 V minus V2 is something, this is, you can see the V1 is much less than V2. So this is a less than the negative quantity. That means I will have to do some work on the system, that is I am working on the system. I am not getting anything out of it, but rather I am working on the system. So this is a one stage expansion that you can see. Now if I carry out the same thing in two stages, then what I can do? That means if I similarly, if you do the same thing, again the pressure volume, and I have a gas, say this is the same V1 and V2. Then this is P2, this is the pressure P2, this is P1, equilibrium pressure is P1. So I want to go from V2 to some intermediate volume V1, V prime. So I need an intermediate opposing pressure, which has to be, say, at this point, say I choose my pressure to be here and volume is this one. So this is some pressure P opposing. So if my pressure P opposing times V prime minus V2, again V prime minus V2 is a negative quantity because V2 is larger than V1, and this is my first stage of expansion, and that is this is the area in this crossed region that gives you this quantity. And then I go from V prime to V1, then I go from V prime to V1. So I will go, final state is V1 minus V prime. Then I say put a pressure, say larger pressure, say P1. So this one from here to here, I give a pressure here. So if I write a P opposing is P1, so this is my final stage of expansion, and this is another shaded area that corresponds to this region, and initially this shaded area corresponds to this region. This is the two-stage compression. This is again a compression. This is two-stage compression. This is one stage, and I see that the area is much larger compared to this. And again, you see that this is a negative quantity, this is a negative quantity, but the pressure terms are always positive. So again, this is a negative quantity, but this is less negative. So the less work is destroyed in two-stage expansion. So less work is destroyed in the two-stage compression. So you see that this is a larger negative value, the negative. This is a negative, but less negative. So less work is being destroyed. So so this is something about the work of expansion and compression, and the main lesson behind it is that if I do some change state of the gas by working on it or getting work out of it, then I have different paths, different ways of doing things, and I see that they can be made quite different in the two cases. So this is an important point that we must always remember. So the idea is this, that if I do multi-stage expansion, I can get more work out of the system. That is something that I will now require for the next discussion, and that is how to carry out in multiple stages this expansion, and ultimately what we can do, the multi-stage expansion can be broken down to some infinite small processes, and if I can do it, maximum. I can gather maximum amount of work out of the system. So that would be the next point of discussion.